Good morning. I would like to thank the organizers, first of all, for the kind invitation to speak here. It's an honor to be at this meeting and also taking care of me in a proper way. We have seen... why is this not working? Yeah. We have not yet seen the beautiful city of Bodrum. Maybe you have, but I haven't. But it's a beautiful city. And it's also a city with a very long history. So it's not only beautiful to see what's on the surface here, but also we would like to know what's underneath the surface to learn the rich history and how everything actually came together here. So it is important to do archaeology. And archaeology you can do in two ways. Of course, you have to dig a pit to go underground. And then you can look at the side wall of the pit that you have dug, and by that learn what's in the ground. Or you recover every element that you pick up while you dig the pit, and you make a 3D reconstruction of what was in this pit. Today I'm going to show you two techniques that I've used, but especially a side wall techniques, to do what I call, sorry for that, atomic scale archaeology. So I'm going to look at what's underneath the gross surface of my structures to learn about the material. And as we have seen, this can be very important for the applications that we have in mind, that we really need to know many details about these structures. And as an example, I want to start here, but that's just for starters, with this well-known Stranski-Krastanov quantum dots. And you can, for instance, think about first growing gallium arsenide, then depositing a thin layer of indium arsenide. You form the so-called wetting layer, which is about 2 monolayer thick. And if you then continue with the growth of indium arsenide, due to the strain-induced mismatch between indium arsenide and gallium arsenide, we start to form three-dimensional structures on the surface that can be further overgrown with material. And this is an AFM image of the quantum dots, the SK quantum dots, before overgrowth. Already we can learn a lot of things about these quantum dots by looking at these AFM images. How many of these nanostructures do we have? What is their size, their shape? But actually, more importantly, I would like to know what these quantum dots look like after they have been overgrown with further material. Do they keep their shape after capping? Can we also look inside the dots? Can we see if there is any composition profile? What is their size after capping? So we really need to know a lot more as just what we can obtain from an AFM image. And for that, I'm using cross-section STM. The technique works as follows. I ask one of my friends in the world who is making good material to send me a piece of that, and in Eindhoven we clamp a piece of that material in a holder, we place it in vacuum, and under ultra-high vacuum conditions we cleave the material, and that we approach with an STM tip, and by that we can make images of the cross-section through all the layers that were deposited on the wafer. And we can look at the nanostructures that are inside. This is an example of a cross-sectional STM measurement on indium arsenide Stranski-Krastanov quantum dots in gallium arsenide. We can see the wetting layer here that is formed before we get dot formation, and we can see beautiful quantum dots in this measurement. These dots gave rise to luminescence at something like 1.15 electron volts. And the people wanted to have the luminescence as a different region, so they annealed the sample, and indeed we see a nice shift of the luminescence. But in my microscopy technique, I also can see now beautifully how the indium atoms have diffused through the material and what the size and the shape of the dot after the annealing is. In this presentation, I want to focus on dots that have been grown by droplet epitaxy. And that's a more advanced technique as what I just described to you. And in the case, for instance, of gallium arsenide quantum dots in aluminium gallium arsenide, the technique works as follows. First, you grow your aluminium gallium arsenide at standard growth conditions. We cool down the surface to something like 200 degrees centigrade. We remove the arsenic flux. That is very important. Then we deposit pure gallium. And there is enough gallium that actually droplets of gallium will form on the surface. Then we open up the arsenic flux again, and then we will crystallize these gallium droplets and to form gallium arsenide. And after that, you can do an overgrowth. This is an example of AFM measurements that were performed on droplet dots that were grown under different arsenic pressures and different growth temperatures. And you can immediately see that the height profiles and the size and the shape of these dots strongly depend on the arsenic pressure that we use during the crystallization of the dots or the growth temperature that was used during the crystallization. So you have a lot of freedom in making these structures. So why droplet dots instead of SK dots? Well, there is a way more freedom in control over size, shape, and composition. Turns out that you can even make rings using these droplet dots and even more complicated structures. In principle, you have a possibility to grow the dots completely strain-free, which can be an advantage for some optical properties. There's little to no wetting layer formation in this process. And most importantly, they have interesting aspects for the creation of entangled photons. And I think that's very appropriate for this meeting here where we talk about quantum related properties and materials. And we have worked in an ITN network on looking at these droplet quantum dots and how they can be used for entangled photons. And I want to measure especially also the cooperation with Toshiba, who is making real-world systems that actually produce entangled photons. This is the outline of my talk. I already have given you a short introduction. I'll talk a bit about now composition control in and near quantum dots. Then I'll show you how we can control the height of these quantum dots and how that affects the emission wavelengths and the PL line widths. I'll show you how local etching can actually occur under the quantum dots and how it can affect fine structure splitting. And I'll end with some conclusions. That was too fast. Here we see one of the very first STM images that we took of a droplet quantum dot. This is a gallium arsenide droplet quantum dot and aluminium gallium arsenide. The aluminium gallium arsenide has this kind of speckled contrast that is due to the local variation in aluminium and gallium concentrations. Where it's brighter, we have a more gallium arsen-like composition. When it's dark, it's more an aluminum arsenide-like composition. Well, here is my self-assembled dot. We see a little bit of the wetting layer, very weak. I can measure the lattice constant along this line, so going from the barrier material into the dot material into the barrier material. This is the height contour that we take with our STM tip. If I measure the distance between the atomic planes, you can see that the lattice constant is exactly everywhere the same. So indeed, these dots are strain-free, as I promised that would be possible. And this is very different from the indium arsenide, gallium arsenide SK dots. You actually make these dots because of the strain mismatch, so these dots will always be internally strained. I'm going. Again, I show here a little bit of the wetting layer. You see it's very weak, so indeed these droplet dots produce hardly any wetting layers. This is also very important if you look at the luminescence from the quantum dots, because the luminescence can couple to the wetting layer, and that is seen as a disadvantage. This is a bit annoying now. It's too slow, I think. What we also noticed is that there is an area above the dot that seemed to be very aluminium rich. You can see it's very dark, and dark means that there is more aluminium in that area. This is a general thing. These are dots that were grown. The previous dots were grown in Japan at NIMS. These are dots now grown in Milano. Here we see the gallium arsenide droplet dots. There is again such an area where we have an enhancement of the aluminium concentration. That effect seems to depend on how much gallium we actually deposit, so how big the quantum dots are. If you go from 1.5 monolayers of gallium to 3 and to 5, we see that this enrichment of aluminium above the dots is enhanced. With atom probe tomography, the technique that we can use to make a 3D analysis of where all the elements are, we can see that indeed this aluminium-rich area is everywhere above the dots. So this is the indium isodensity contour. So here is my gallium contour. Here is my gallium arsenide quantum dot. This is the aluminium contour, and here we see the aluminium-rich areas. And you can see that indeed this aluminium-rich area overhangs like a little cloud over this hill that is the quantum dot. And remind, please, this is in the order of 20 nanometers. You also can look at the profiles that we can take here right through the center. We can look at the arsenic counts, that's 50%. Well, that should be the case. Then gallium goes to 50%, so inside the dot, indeed, we have pure gallium arsenide. And above the dot itself, we see that the gallium concentration drops, the aluminium concentration increases. So here we have the aluminium-rich area that is shown by this blue cloud. What is the process that is responsible for this aluminium enrichment above the dots? If you have formed the dots and you start to overgrow the material, the surface wants to flatten out. So there is mass transport of atoms that arrive in the area here above the dot that will go to the sides in order to level the structure. Now, gallium atoms are more mobile as the aluminium atoms, and that leads to this net enrichment of aluminium above the quantum dots. Can we suppress this effect? Yes, we can, and for that we use double capping with flashing together. So here is my substrate on which I've grown the dot. I do a first capping, but the first capping has a height that is smaller than the height of the quantum dots. Then I do a flash, that means I raise the temperature and I evaporate everything off from the surface. I get a flat surface here, and then I can do an overgrowth with a second capping, and then we have a structure like that. Did it work? Well, here is the dot grown in the standard fashion. We see the aluminium-rich area above the dot. Here we have done this 2 nanometer cap. This, the first capping layer was 2 nanometers thick. Then we do the flash. Indeed, all the aluminium enrichment is gone. But you also can see that the top of the dot is rather flat. And we have a height, if you would measure it, is exactly 2 nanometers. We also can do it with 4 nanometers. And that way you see that you also have now a way to control the height of the dots. And that brings me to height control of quantum dots that you can obtain by this double capping and flashing method. Here are again a few quantum dots that we grow. This is a 1.5 monolayer gallium deposition. And here we have a 5 monolayer deposition. But we can see that we can control the height by the capping that we do in the material. And indeed, we see that there is a nice control how we can limit the height of the quantum dots. Without this double capping method, we already noticed that you can control the height of the dots also by how much gallium that you deposit, or by controlling the temperature and the arsenic flux during crystallization. And this is work that we did together with the colleagues in Milano. And I already showed you this image there. We see that the quantum dot height and the profile actually is strongly dependent on the arsenic pressure during crystallization, or on the growth temperature during crystallization. And I can characterize these profiles with the facet angle, so that's the angle of this facet that we see over here. That strongly depends on temperature and arsenic pressure. And the aspect ratio, that's the height versus width. And if we look at the aspect ratio now as function of these parameters, we see there is a clear dependence, both in the pressure series, the arsenic pressure, or in the temperature series. The colleagues in Milano were able then to model this process, and the modeling of the process is based on 2 crystallization effects that are important in this work. Here we start with the surface of gallium arsenide. We have the gallium droplet over here, and now we introduce the arsenic to crystallize the dots. It turns out that the crystallization first starts at this liquid-solid interface. Here we have the gallium liquid on top of the solid gallium arsenide surface. Arsenic atoms that come in give rise to crystallization in this area. So from there it will grow and expand. But also we have gallium atoms that actually can still diffuse, for instance as function of temperature, but also as function of the arsenic pressure, to areas outside this crystallization area, and by that broaden the dots. And these two processes were modeled, and with that they were able to come with a universal relation for the facet angle and the aspect ratio as function of crystallization temperature and arsenic pressure. And you see that nicely can be described over here. So there is a good understanding of which processes are involved in this gallium arsenide crystallization process. Again now with the colleagues at NIMS in Japan, we looked at gallium arsenide quantum dots in aluminium gallium arsenide. In this time, the height of the dots was controlled by depositing more gallium. And here we see the height of the dots as we measured it with cross-section STM. There is a nice height relation depending on the amount of gallium that has been deposited. And there is a base length also which is more or less constant, where you can see that this base length is more or less constant, but the height can be varied very nicely with the amount of gallium that is used. By the way, different from before was that there was an annealing step after the dot formation process, and that actually gives rise to the shape that we see here. If you then look at the PL measurements for these dots, on the left I show you the macro PL, and the macro PL shows a clear shift of the PL luminescence as function of the amount of gallium that has been deposited. And then in the micro PL, this broad peak actually breaks apart into individual peaks that are related to individual dots in my micro PL spot. You can measure the widths of these PL lines, but already from this graph you can see that the widths of the lines here for the 7.5 monolayer dots, the higher dots, the width is much higher as for the dots which are not as high. So here we have the line width of the quantum dots as a function of emission energy that is directly related to the height of the dots or how much gallium that we deposit. And for the higher dots, the line width becomes smaller. Why is that? Well, the idea is as follows. Here is my quantum dot, and in the quantum dot I have my exciton consisting of an electron and a hole being trapped in the dot. And if I have a dot which is very high, I can polarize the exciton very easily. I can pull the electron and the hole apart very easily. That's not so simple when the dot is not so high. So the stark effect that you have, the detuning of the luminescence, is bigger when you have a higher dot as when you have a lower dot. And now the cause for the fluctuations that we see are in fact charges on the surface that change their charge state. By that there is an oscillating electrical field, and through the stark field that couples to the detuning of the exciton and giving rise to the broadening of the peak. So if you want to have droplet dots that show long coherence or a long lifetime, it's important to grow quantum dots with a low height, or of course try to avoid these fluctuating impurities on the top of the surface. That's the other way to go. There was another surprising effect that we saw when we were looking at these droplet quantum dots, and that was the effect of local etching that I would like to describe to you right now. This is again a gallium arsenide droplet dot in aluminium gallium arsenide. This is the surface on which the gallium droplet was formed and which was subsequently crystallized. But you see that underneath the dot there is a gallium arsenide rich region. And the reason for that is that the gallium droplet can actually etch into the underlying aluminium gallium arsenide. This is a process that was described by colleagues from Hamburg. And here we see this effect of local etching. The indium droplet liquefies the gallium droplet, why do I say that all the time? The gallium droplet liquefies the aluminium gallium arsenide underneath. By that, gallium and arsenic atoms get picked up and go into the dot. If you look closely in the gallium arsenide dots, we can see individual dark features. And those are individual aluminium atoms. These aluminium atoms have been brought into the dot by this local etching, which pulls up aluminium atoms in the etching process. And by that is contaminating your pure dot. A beautiful example is also shown over here in these dots from Milano. A gallium arsenide, almost pure dot here, but sometimes these dots start to etch into the substrate. We see here now that there is a concave bottom, and we see lots of aluminium atoms inside the quantum dot. So there is intermixing and etching often go together. With that knowledge, we were actually, we came into contact with the group in Cambridge, Toshiba, in the network, and they were working on indium arsenide, indium phosphide droplet quantum dots, which were grown in Sheffield. John Heffernan is here as one of the growers that was involved in that. And the nice thing for these indium arsenide, indium phosphide droplet quantum dots was that they could actually tune them to the wavelengths for communication of 1.55 microns. And they use these quantum dots for the production of entangled photons. The process is as follows. Indium droplet formation occurred at 400 degrees centigrade. Crystallization was about 500 degrees. And there was a capping with 30 nanometers of indium phosphide, followed by even more indium phosphide. What they noticed in these quantum dots is that the fine structure splitting is very small. And let me take you through that a little bit. If you want to create entangled photons, you have to create a bi-exciton state in your dot. So we fill the dot with 2 excitons. And then actually when the photons come out in a cascade manner, you have 2 paths for the recombination. And depending on the asymmetry of the dot, so whether it's a square or an elongated square, there can be some splitting, some polarization splitting of this intermediate state. The more symmetric that you make the dot, the smaller this asymmetric splitting will be, and the better entanglement of the photons that you will have that you create in the 2 steps. So it's very important for photon entanglement that you have a symmetric dot where this fine structure splitting that we see here, or polarization splitting, is as small as possible. This is the work from the people from Sheffield and Cambridge, and they looked at SK dots. And the SK dots, they have a rather large fine structure splitting, as you can see along the axis here. This is the emission wavelengths. They have a rather large fine structure splitting. Also here in the histogram you can see it. But then when you go to droplet dots, either from indium arsenide on indium phosphide, or from gallium arsenide on indium arsenide on gallium arsenide, we see that the fine structure splitting is way smaller, but the advantage of the indium arsenide dots in indium phosphide is that they emit at 1.55 micron. With our cross-section STM technique, we could beautifully resolve their dots, and already from this you can see that they look rather pure in indium arsenide. So in order to prove that better, we looked at the lattice constant profile over this line here, so measuring the distance between the atomic planes. And we made an estimation of what the profile should be, the lattice constant profile. That's the simulation here in red, and the measurement is shown in dark. And the simulation assumes that the dot consists of pure indium arsenide. So I think we see that indeed it's possible to grow pure indium arsenide quantum dots on indium phosphide in this technique. A bit unfortunate was that we saw this edge pit formation very often. Something like 60% of the dots showed an edge pit underneath. And, well, the size and the position of the edge pit was very different and differed from dot to dot. It was also interesting that we saw that if you have a bigger edge pit, that the dots seem to be smaller. Of course, that's related to the availability of the indium that you have in the material. We were worried that this edge pit actually also has an effect on the fine structure splitting. And if you break this symmetry by pulling the electron and the hole laterally apart by this edge pit, that actually would increase your fine structure splitting. So we looked at, and this is a modeling we did with the group of Michael Flatte in Iowa. We looked at quantum dots with an edge pit underneath, and first we had an edge pit right under the center of the dot, and we increased the size, and we saw that that actually reduces the fine structure splitting. So that's good. That's nice. But when the edge pit moves to the side, then actually increases the fine structure splitting, and that is bad. And because at the moment we have no control over where we actually get this edge pit, it's better to prevent the formation of edge pit than to use it to your advantage. So for that, we worked with the team in Sheffield on looking at dots where we could possibly prevent this edge pit formation. The dots where we saw the edge pit formation were grown below 500 degrees centigrade. And by going a little bit higher in temperature, we actually could remove the edge pit very successfully. But it came at a price. And the price was that now there was a lot of etching next to the quantum dots. You can see already here there is some kind of steep edge, where here we have the pure indium phosphide, but here's the intermixed wetting layer, and actually our dots stand on a kind of terrace. There's trench formation around the dots. I've put circles around it here. Here you again can see these trenches that form around the dot if you grow at 500 degrees centigrade. Something you also do not like and would like to prevent. And with further work, we showed with the people in Sheffield that you actually, this is the processes that we have. Below 500 degrees centigrade, we have the local etching underneath the dots, giving rise to these edge pits, whereas for growth above the 500 degrees centigrade, the indium phosphide surface becomes unstable. Indium atoms can move towards the dot, towards the droplet. Phosphorus atoms can escape into vacuum, and that actually gives rise to this etching of the material next to the dot. Both processes can be prevented, and for that you only have to grow a indium gallium arsenide layer underneath. Presently we're still looking at how thin this indium gallium arsenide layer might be to prevent it, but actually that turns out to be a very effective way to suppress the etching underneath the dots or next to the dot. Before I go to my conclusions, I would like to acknowledge the work of many people involved in this work. It's work that has been carried out over many years, but especially my PhD students here in red contributed a lot to that. And of course, my partners here in theory, Michael Flatte and Craig Pryor, the group in Sheffield who grow the indium arsenide, indium phosphide dots, the team at Toshiba who supported us. Some of the early gallium arsenide, aluminum gallium arsenide quantum dots came from NIMS in Japan, and then some of the later work we did with the Milano team in the European network. Let me finish by showing you what's learned. I think we have shown there are various modes for shape and size control of droplet dots, and especially we can control the emission wavelengths. And I think for communication it's very important that we can operate these quantum dots at 1.55 micron. We have observed unexpected and unique effects such as aluminium enrichment above dots. I've shown you etching below, next to and underneath the dot. I've shown intermixing in droplet dots, but I also showed you how we can actually control all these effects, and that we can make now good quality, clean quantum dots. We also have learned how size and shape of the dots affect the line widths in PL emission, and if we talk about entangled photons, that will improve our coherence lifetime if we have a narrower line width. And we have also shown how you actually can affect anisotropic splitting by edge pits and how that can be detrimental for entangled photons. So we can actually improve entanglement by reducing this edge pit formation. And with that, I would like to thank you for your attention.
Thank you very much for a great talk. We have a question right here.
Thank you very much for your nice presentation and for your persistency. I remember that you have been doing this cross-sectional STM over a long time, and I admire the recent achievements. My question contains two elements. First of all, the same process of local epitaxy produces drilling, and if you continue this process, you may have quantum rings in the same way.
Yep.
Where are you interested in investigating the structures of another topology? And second question, what are requirements for statistics of samples? How many dots you need in order to get statistically representative results of cross-sectional STM? Thank you.
Well, answer to the first question, our interest was not in rings this time. Although I know that droplet epitaxy is very suited to make beautiful quantum rings or even multiple ring samples. They have shown that you can make nested rings. We were not interested in that at the moment. Concerning statistics, well, when we get the samples, we are very much determined by how many quantum dots per square nanometer or per square micron we have in the sample. We like to see as many as possible dots. Typically, we look at 50 to 100 dots in order to build our statistics.
Thank you.
We have a question up here, and then Herman.
Did you also try to probe the confined electronic states and their spatial distribution in these buried dots by scanning tunnel microscopy?
Yeah, we tried, but not very successful. So people have shown that it's possible. With the SK dots, I think there's beautiful examples of teams that have done it. We have not tried it on these samples. We did one go. We're not too happy with it. Didn't see the need at the moment to go forward with that. So this is why I did not push that any deeper. But yes, it's possible, and it's very nice.
Thank you. Thank you, very nice. When you talk about pressure and temperature effects on the growth of these structures,
yeah,
can you control the interface sharpness and the cooling rates so that would give you access to control the structural order and segregation, for example?
Let me try to answer your question. I don't know whether I have the right picture for that. No, then I have to go into my reserve slides, which is a bit different. I can show you that afterwards. But in principle, yes. And especially you can see that in the wetting layer. I mean, in the wetting layer, in the case of the indium arsenide, indium phosphide structures, this is an exchange process where phosphorus goes out, arsenic goes in, so then you make indium arsenide in between the quantum dots due to exchange. We do see these layers, they do form, and in the case of SK dots, you really need that wetting layer, so there that wetting layer is much more important than in the case with the droplet dots. I can show you that. But also we see the segregation of indium out of these wetting layers. There's typically an exponential tail of the indium distribution in the growth direction for these wetting layers. But that's something we have done many, many times before.
Do you see how the pressure and temperature affect?
We have not done that experiment, but it's a good suggestion to do. Thank you. Yeah.
Well, if we don't have any more questions, let's thank our speaker.
All right.
Many thanks for your great presentation.
Thank you very much.